turns to sun rays, and on we'll go through the wastelands, through the highways, and on we'll go to that light of the rising sun, to that.
Good evening and welcome everybody. This is Obi-Wan Piz for Simplix Pachinko, and we are doing some math tonight. So, starting in on night 4 of cracking the GRE math test. I suppose that should be part of the title. Right. So, on Wednesday, we went and, what on earth is going on there? Okay. We went and talked about the fundamental theorem of algebra and some of the basic root theora that existed for polynomial functions. So here this was find the monic cubic polynomial p of x that has real coefficients such that the equation p of x equals 0 has 1 and 2 minus I as its roots. So in this case, we said monic was where a sub n, our leading coefficient, is going to be equal to 1. We also said that we want those roots and those roots only. So only get those zeros. So 1 and 2 minus I should be the only zeros that we know of. However, logically consistent with making sure that we have real coefficients is the demand that since we have a complex non-real 0, that we also have its conjugate. So the conjugate root theorem said that we needed to also have 2 plus I as one of its roots. That is the minimum degree polynomial for which we can find these two particular zeros. Alright, and then we got p of x is equal to x cubed minus 5x squared plus 9x minus 5, which is exactly what's in the book. Okay. Another example below it is for the equation x squared plus bx plus c is equal to 0. The sum of the roots is 3. Sum of the squares of the roots is 1. And specifically, this only wants the numerical value of c. So what is the, essentially in this case, it is going to be the product of the roots, possibly negated. Yes. Negation of the product of the roots. No. Never mind. Because they could have the same sign as each other and end up positive no matter what. So, yeah, product of the roots will then have the exact same sign, but numerical value will the numerical value of each of them will be flipped. Okay, so the sum of the roots is equal to 3. We know that this is going to break into something that looks like x minus, let's go with m times x minus n is equal to 0. We know this again because in our factorization, like we talked about before, this is monic, so we have a 1 for our a value, and therefore we have 1x times 1x must be in that order. And then our two roots m and n, right? M plus n is equal to 3. M squared plus n squared needs to be equal to, that is not c, needs to be equal to 3. There we go. And m squared plus n squared must be equal to 1. In addition, when we multiply this out, we get x squared plus, parentheses, a negative m minus n times x plus, here, negative m times negative n is just mn is equal to 0. That's not what I want. There we go. Let's just change those here. Okay, this was our system of equations that we created from the original argument of the problem. And so here we see that negative parentheses m plus n is going to be equal to b. So m plus n is negative b, which is also equal to negative 3. Sorry, m plus n is equal to 3. I'm all right. And therefore, b is equal to negative 3. All right, this is not the answer. However, it is a nice little step that we can take to get through all this. Okay, now the sum of the squares of the roots is 1, so m squared plus n squared must be equal to 1, while m plus n is equal to 3. So in this particular case, we can simplify this to another quadratic. So we're solving a different quadratic equation, but it, you know, if m is equal to 3 minus n, then 3 minus n parentheses squared plus n squared is equal to 1. This is going to be n squared minus 6n plus 9 plus n squared is equal to 1. This is 2n squared minus 6n plus 8 is equal to 0. It's hardly fair, but you know what? It works. In this case, right, this is going to give us another quadratic equation. This is going to say that we're looking for factors of 16, which are 1 and 16, 2 and 8, 4 and 4, which, when they have the same sign and the larger one is negative, therefore both must be negative. That must add up to negative 6. Well, unfortunately, right, these add up to negative 8. The ones above are negative 10 and negative 17. So we're getting closer as we start moving down further and further. But the problem is that we now don't have room for a negative 6 for a b value, which means that our c value, the plus 8, is moving this up too far in order to get an actual, in order to get a real answer. So we can't factorize this. All right. And just to check it, right, b squared minus 4ac is going to be equal to 36 minus 4 times 2 times 8, which is going to be 4 times 16 is 64, subtracted from 36, which is less than 0. So this is going to end up getting us something that we really should use the quadratic formula for in this case. So n is going to be equal to, this is negative b, negative negative 6, plus or minus square root of negative 6 squared minus 4 to 8, which, again, we already know what this is. Or at least, I didn't actually do it out. It's fine. Denominator is 2 times 2, so we get a 6, plus or minus square root of. This was, again, 36 minus 64, so we're going to get a 28, negative 28, over 4. This is equal to 6 plus or minus. 28 has a 4 in it, which is going to become 2, square root of 7, and we're going to get an I for the negative on the inside. All divided by 4. Divide all the things by 2, or, in other words, factor out a 2 from the top. 3 plus or minus root 7 times I, all over 2 times 2. Get rid of the 2's, and we get that n is equal to 3 plus or minus I root 7 all over 2. And this is not really all that surprising at this point. Whatever is going to happen, if we pick the positive one, then m is going to be 3 minus this thing. What does that do? Well, that's going to make 3 minus the 3 halves. But 3 minus 3 halves is 3 halves. So the number, the real portion, is going to stay the same. And then the negative is going to apply to the I term as well, which is going to flip that to be negative. If, on the other hand, n is the negative one, then the exact opposite happens with m. We get 3 minus our 3 over 2, which is, again, 3 over 2. And then the negative applies to the negative. It's going to switch it to become the I term, positive I term. So that means that m has to be equal to, bump this up a bit, m has to be equal to 3 minus plus I root 7 over 2. Again, it doesn't matter which one's which. So, as long as we acknowledge that we have two numbers here, they are complex conjugates of each other. And without loss of generality, m can be just equal to 3 plus I root 7 all over 2, and n is going to be equal to 3 minus I root 7 all over 2. So, without loss of generality means that it doesn't matter which one you pick, you're just going to get the other one for the other one. Whichever way you pick, the laws of mathematics are still going to hold. All right, and then we said that mn is going to be c. So from above, m times n is equal to c, which is equal to, here we get 3, that's fine. 3 plus I root 7 all over 2 multiplied by 3 minus I root 7 all over 2. Okay, so what does that do for us? In this case, right, we're still going to get c is going to be now over 4, and then the top ends up being a product of the numerators. So here we can get 9. The first one is going to be a plus 3 times I root 7, and the other is going to be a negative 3i times root 7. So it's the same thing, right? Either way we go. This is still going to end up eliminating this term and becoming 0. And then we get I times negative I, which is going to be a negative 1, nope, root negative 1 squared. So now it's just going to be a negative 1. So this is going to become a positive, and root 7 times root 7 is just 7. So this is now going to be 16 over 4, which is 4. C equals 4. Woo! All right. And to check. Right, r squared plus r1 squared plus r2 squared is equal to, they expanded it out. They plugged in the appropriate values with b and c in the appropriate locations. And they got that r1 squared plus r2 squared is equal to b squared minus 2c. You know, it's not quite exactly what we did, but it's the same kind of idea. So for this question we have negative b is 3, and b squared minus 2c equals 1. And since b equals negative 3, super simple, we then get negative 3 squared minus 2c is equal to 1, therefore c is equal to 4. They did it way easier. So let's... this would be a time saver. They said that we used a quadratic formula, so it sticks kind of with the theme. However, at the same time, they did a method which definitely saves time on a standardized test. So what they used was that r1 plus r2 squared is equal to r1 squared plus 2r1 r2 plus r2 squared. Then they said that r1 squared plus r2 squared is going to be equal to shift the extra term over, r1 plus r2 squared minus 2r1 r2. And they said that r1 plus r2 was our m plus n, which is equal to b. Negative b. But then all of that is still squared. Minus twice. We did this up here. We got that m times n is equal to c. So r1 times r2, m times n. Right, is equal to r1 squared plus, well, this is again m squared plus n squared, which we said, well, the sum of that stuff was just 1. From the beginning, right? And then this is going to be b squared minus 2c is equal to 1. We know that b was negative 3 minus 2c, c, not 9. This is 9. Right, subtract 8 from both sides. We get a negative 8 is equal to negative 2c. Divide by negative 2. And therefore, c is equal to 4. So yeah, way easier method if you can remember that sort of, well, if you can see the connection. Really, that's kind of what they're going for here, is do you see the connection between these relationships? So I was much more locked into what we were doing over here, which is, hey, let's do some quadratic stuff. If we bring these two linear equation and a quadratic equation together, we can then create a different quadratic equation in one variable, and then we can solve that. So, yeah, significantly easier. All right, one more example here. The equation. Right here. The equation. 3x to the fourth minus 7x cubed plus 5x squared minus 7x plus 2 is equal to 0 has exactly two rational roots, both of which are positive. Find the larger root's value. Right? So, we know from the rational roots theorem that if we take all of the factors of our final term, the constant term, final when it's in proper deducting. No, that's wrong. Not reducing. Come on. Come on. Descending. If we're in proper descending order of powers, so x to the fourth, x cubed, x squared, x, and then x to the 0, our constant term there, 2, has factors of 1 and 2. The denominator is going to be represented by our lead coefficient, which is 3, which has values 1 and 3 as its factors. And then we can do this as plus or minus. However, we said exactly two rational roots, both of which are positive. Therefore, we don't need this negative 1 at all here. Right, so what are the possible zeros that we could get for this? All right, we could choose, this is going to make a Punnett square essentially. Could choose 1 over 1, which is 1. We could choose 1 over 3, which is a third. We could choose 2 over 1, which is 2, or 2 over 3, which is 2/3. If you want it in, proper form, I guess, we'd start at the bottom and then work our way up in terms of value. It doesn't really matter, it's just one of those things. Okay. So at this point, we look at this and say, okay, these are our candidate zeros. and there are only 2 which are positive rational zeros. So working from here, we could do a number of things. One is look on your calculator. Okay, so literally if we just go to Desmos, right, we can narrow this down almost instantaneously as long as you actually plug this in, quickly. 3x to the fourth, I'm not going to do it quickly because I don't remember. -7, 5, -7, 2. Right, 2 rational zeros, both are positive. That's all we've got. The values max out at 3 in either the positive or negative direction. So we're good, right? That's as far as I can go on this side, and that's as far as I can go on this side. We found the 2, they're both positive. So they appear to be at 1/3 and 2. So instead of messing around, you say, okay, look, I verified this on my calculator. It appears that the zeros appear to exist at x equals 1/3 and 2. But we totally don't absolutely know that for a fact. Therefore, what we're going to do is check our synthetic division and check with the remainder theorem. Right, so here we're going to do 3, -7, 5, -7, 2. Let's check 2 first. So oftentimes if you've got whole numbers in here, it's pretty good to keep it as whole numbers. It won't matter because if you do it as if you do it as a fraction, so if we end up with, trying it with 1/3 first, then you can end up, you just end up with extra constants, or common denominator. Nope, common factor. You'll have a common factor of the denominator of the factor you just used. So here with a 2, right, the common factor is going to be 1. So again, here we're taking the previous number, which is technically a 0, and multiplying by 2, we get a 0. We don't write this normally. And then we add down. So this is going to be a 3. Now we multiply by 2 going up. This is going to get us a 6. And then we add going down. This is going to get us a -1. Again, repeat, this is going to get us a -2. Add down, this is going to get us a 3. Multiply up is a 6. Add down is a -1. This is getting repetitive. And then multiply by 2, we get a -2. Add down, we get a 0. That's what we want, because again, we started with x to the 4th, and then this was a constant over here. When we divide out by a factor, when we divide out by one of our x's, this is now going to become x cubed. And then this is going to be our constant here. And then this is going to be a remainder. Right, so because the 0 is a remainder, it divides evenly. So now we have an x minus 2 as a factor that's been pulled out of this entire function. So in fact, right, let's just write this real quick. This is going to end up being x minus 2 multiplied by x. Okay. 3x cubed minus x squared plus 3x minus 1 Okay, and then we are going to divide by a factor of 1/3. This is x minus 1/3. Which, again, multiply up, add down, we get a 3. Multiply up, we get a 1. Add down, we get a 0. Multiply up, we get a 0. Add down, we get a 3. Multiply up is a 1 by 1/3 is a 1. Add down is a 0. So now this is going to be an x squared term. Here's our constant. And then the remainder on the 0. So then this gets us x minus 2 times x minus 1/3 times 3x squared plus 3. Now I could take this over here, right? Move the factor of 3 from 3x squared plus 3 over to x minus 1/3. And this ends up with x minus 2 times 3x minus 1 times x squared plus 1. Okay. Find the larger root's value. So we know it's 2. On the exam, what are you going to do? Plug it into your calculator, find the root. All right, it's going to take 0 effort. But if you need to actually show work, like if you're doing this for a candidate interview or anything else for that matter, then you should follow these steps going through, right? If it's just for the GRE, like who cares? Just get the answer, move on, fast as you can. But if you're doing this, like I said, for a candidate interview for a job, or if you're trying to teach a student actually how to do this for real, not just for some random standardized test like this, then you know you've got to know the method. If anyone has any alternate methods than the things that I'm doing, that may not be 100% like, you know what? Even if it's standard, I will take anything just to try and understand what it is, and then let you know whether or not your chosen method aligns with my teaching values. But you know, most of the time it's going to be fine. Most likely, if it's something like, hey, this is what I do, and I just do this because it's easier, there is the possibility that in just doing this kind of process, you're going to lose some sort of generality, or there's going to be a reason why later on it's actually going to be easier to not make it expeditious and try to actually do the larger version of that method. All right. One of the other reasons to do it the way that I had just done it, if you're actually, right, if you're actually trying to do the problem and not just trying to rush through it for a GRE, this version also gets you the other 2 roots. So you can see right here, x squared plus 1 is a quadratic. X squared plus 1 equals 0 is going to, we should probably make that equal to 0 here. Right, so x squared plus 1 equals 0 is going to get us x squared equals -1, which means that x is equal to plus or minus the square root of -1, which is I. So x is going to be plus or minus I as well, which, again, you can look at this and be like, well, yeah, it clearly is not going to be a real number, and therefore we can't count it for what we were looking for here, right? We were just looking for the largest real root. Okay. Okay, so logarithms. one of the other things that get people really confused about a lot of stuff. Where we want to go with this is that we have that these are inverse functions of our exponential functions. Right, so when we look at exponential, we're going to get something like, and in fact, not even y, let's do, right, e1 of x. Which is equal to, let's just do 2 to the x, right? Make it nice and easy. What we have here is that at e equals 1, we're just going to get 2 to the first. E equals 2, we're going to get 2 squared, which is 4. And at 3, we get 2 to the third, which is 8. Now, we could try and work out all sorts of stuff. We could say, like, how do you know the exponents when you get them to be 0 or negative? Like, what do you get? Okay. One of the easiest ways to do this is just start counting backwards. So what are we doing as we're moving up the list, right? From, again, if we want 4, it's going to be 2 to the fourth, which is 16. 16 to 8 to 4 to 2, we're cutting these all in half. So here, right, 2 to the 0 is going to be what's half of 2 to the first. What is half of 2? That's just going to be 1. And then 2 to the negative first, we can go either way with this again. Either this is going to be 1 divided by 2 to the first power, or you start from 1 and you divide by 2. So you get a half. And again, 2 to the negative second, do the same thing. Either it's 1 over 2 to the second, which was 4, or it is half of 1/2. So 1/4. So when we talk about the logarithmic function, again, we talked about how to find inverse functions. This was something where we said, okay, we're going to that was weird. What we're going to do is say that we've got y equals e of x is equal to 2 raised to the x power. If we take the e inverse function of both sides, then on the left, we just get x. And on the right, what we have is e inverse of 2 to the x, which is going to get us our I have notes on this, and I just blanked in my mind what I was going to do with that. Oh, that's terrible. Okay, so let's look at it. And we say what the inverse function does is we're going to undo what is inside the parentheses, which was our exponential function. And so what we're saying is we want to do the opposite of the exponential function. So in the exponential function, we start with an exponent, right? So e is something that takes an exponent input and then maps it over to an exponential term. So x then becomes 2 to the x or whatever else we've got. So E inverse is going to take in reverse an exponential 2 to the x and then tell you what the exponent is going to be. That gets you that thing. Now we do have to specify which particular exponential do we want to talk about, because when we just jump into this later on, it's going to be like, well, yeah, sure, you could take a log, but which log? Do you want your exponential? And especially if it's something like, you know, take the log of 3. Okay, cool. Is that a log base 3 of 3? In which case it's just 1, because that's 3 to the 1 is equal to 1. Or is it going to be like, well, the log of 3 in something that looks like 5 to the x is going to need a small exponent in order to bring that number 5 down to 3 by raising it to a power. Right, we're going to have to take some sort of root of it in order to make that work properly. Okay, so in this particular case then, we're looking at this and saying that we need, you know what, let me get my other, yeah. Okay. Logarithmic functions. Change of base. How do I introduce this? Yeah. Well, nuts. This is too old, unfortunately. This is... what year is this? 22. So this is not my latest set of boards, which did have a slightly different way of introducing logarithms as inverse functions, specifically inverse functions. And I used function notation to do it. Oh, you know what? Here it is. This is a prototype, but it's still pretty close. Okay, so we let... Right? Let e of x equal 2 to the x. Then, taking the inverses of both sides, I did it on a much more complicated problem, so it made it more interesting. Right, the exponent on 2, that gets us 2 to the x, which is true, but rather unimportant, or rather uninteresting. So this gets us the idea of logarithms. Right, because what if we want a base of 3 or pi or whatever else we want to think of? Right, we will not just be able to throw something into a calculator without specifically thinking about what base do we want on this thing. Anyway, in order to do logarithmic, then we want the e1 of x to be equivalent to our new inputs of x. That should really be e1 of, like, I guess e1 of 2 to the x. e1 inverse of 2 to the x. That's on the other side. Oi. Okay, this stuff over here should be e1 inverse of 2 to the x. Whereas this should be our new input. Which is going to look like 2 to the x from before. Alright, so we get this 1/4, 1/2, 1, 2, 4, 8. And then our outputs are going to be the inverse function values of -2, -1, 0, 1, 2, 3. Alright, so if we want to graph this, right, we take this, get rid of the sloppiness. Right, we know for a fact that we're not going to get any negative values. In the x direction. And we'll get limited negative values in the y direction. Although in this case, right, it could be anything. And essentially what we're doing is, as we're counting either up or down in the y direction, we're going to be multiplying in the x direction. Give or take. Right, so when x is 1/4, which is like way in here, that means that y is going to be 2. So we get a point here. When x is 1/2, which is about here, we're going to get a y value of -1. When x is 1, we get a y value of 0. And then we have to, again, we keep just increasing our y values here. So when y is 1, x is going to be 2. When x is, no, when y is 2, x is now going to be, when y is 2, x is now going to be 4. And when y is 3, x is now going to be 8. And then if we feel like it, right, when y is 4, x is going to be 16. Yeah, give or take. So we get something that looks like this. This is y is equal to the inverse of, and we could just rearrange our variables. Again, our input values are just going to be x's, and our output values are just going to be y's. So they get replaced in that way. Let me see here. If we go back to function inverses. Right, it's the way that I'd really done it before. The way that I usually talk about inverse functions is that we introduce the concept via right, x's and y's, but here we have the E inverse of y is then equal to x, and then we state, like, you know, what function it was that we were using, or state its appropriate equation, and then E1 inverse of y, we just kind of like change the variables, and our all of our instances of y's become x's. So it's not really how I wrote it here. That's going to be a pain. It's fine. So if we did like e of x equals y equals 2 to the x, right? Then we're doing e inverse x equals e inverse of y is e inverse of 2 to the x. I think that's throwing me off because it's now an x just by itself. It's not usually how it works. Fun times. Because typically we solve for x. So once we've solved for x like we did here, then we just like let e1 of y replace that, and then we've got an equation that is just based in y, typically. Oh, yeah, I mean e inverse, I didn't specify it. Ads are about to start in about 2 minutes. Right, this is log with base of 2 of y, which is equal to x, which is equal to e inverse of y. Right, and then if we just concentrate on these things, e inverse of x then is equal to log base 2 of x, which is equal to y values, output values. It does look to some people like, oh, you changed the, like you swapped the variables. That's not really what I'm doing. It's that we're reassigning the variable according to function notation. So e inverse of x is going to be replacing e inverse of y in the previous step. Okay, gonna take a 3-minute break, and we'll see how things are doing around the house, and be back in a little bit. So thank you very much for sticking around, and see you in just a bit. Good evening, welcome back. Right, so we're looking at the logarithms. And this means that if we just start with the idea that we can have a logarithm with base b, whatever base this is, of x, this is going to mean that our, again, input is an exponential. Which then we want to put into base b, even if it doesn't currently have a base of b. We just sort of imagine that it does. And our output is going to be the exponent. So, if we let x be equal to b to the mth power, for example, then f at x is going to be equal to log base b of b to the m. Right? Reframe it. What exponent on a base of b gets us b to the m? So whatever x value you picked, even if it's not a nice exponential, right? All x's can be rewritten as b to some mth power. So the output here, f of x, is going to be what exponent on the base of b gets us b to the m? The answer is m. Now, it's not that simple. You can't just come up with some sort of m value, but what we're saying is that here we're saying that we can rewrite x, any input we want, as b to some power. So we're just trying to find out what is that power. This does help us in that we can say, all right, well, we do know some facts about exponentials and therefore by logs. We could say that we know that if we're doing this as b to the 0, b to the first, b squared, b to the third, b to the negative first, b to the negative second, etc., these are going to be our nice inputs. The nice x values that we can get. And then our f of x values are going to come back very nicely as negative 2, negative 1, 0, 1, 2, 3. Right? That's our goal. If we can find that, that's awesome. Right? That also means that we can graph this super nicely. Right? With a b value that is greater than 1, we're going to end up with, something like a 1 here. That's b to the first here, b to the second here, b to the third here. And then we end up with 1, 2, 3 out here. So, nope, that's wrong. Bring those down here instead. So, 1, 0, b to the first, comma 1, b squared, 2, b to the third, 3. Okay, and then b to the negative first is going to be here, b to the negative second is going to be here, whatever it's going to look like. Roughly speaking, something that looks like this. So those are going to be the nice values that we want to go for, no matter what we're doing, no matter what b is. Now if b is less than 1, then that's going to tell us that as we raise to higher and higher powers of b, our those values are going to get smaller and smaller. So that is actually going to be okay. We'll rewrite this here. This is b to the negative first, b to the negative second, etc. With b less than 1, when we get out here, this is going to be, again, 1. This is going to be this is b to the first power. That is going to be b to the second power, because when you multiply by something that's smaller than 1, it itself is going to get smaller. So then b to the negative first is going to be out here. B to the negative second is going to be out here. And b to the negative third is going to be out here. So we get a -1, -2, -3. So we're going to get something that looks like this. If anyone has any other questions, please interrupt me or whatever. All right, so these are going to be the like prototypical logarithmic functions. Right, do notice that if we put a negative on the outside of the equation, right, if we put a negative on the outside of the log, that's going to effectively, just as we're seeing it here, flip it vertically. Because that's going to flip all of the exponents to a negative compared to what we had in the other example. Right, so y equals negative log base 2 of x is going to be equivalent to the log base 1/2 of x, or it's going to be the equivalent of the log base 2 of x to the negative 1. Right, it's taking all of our exponents and flipping them negative, which you notice that that's what's happening on the x-axis. Right, all of these exponents here have opposite values as all of these exponents here. So there's a number of ways that we could argue this point. I mean, literally just happened there. Right, we're going to allow the base to be flipped or to have an inverse, multiplicative inverse, or we can have the inputs have a multiplicative inverse. Right, these are all the same as each other. So, pretty cool stuff. All right, we could do all the same verification of identities for logarithms using the idea that we did up here, where we allowed b to the m to represent our x value and various other things. So, could do that. Not sure we want to. Then there's also the graphing method that I use, which typically is going to be something like y equals a times the function in particular that we're using with whatever. Oh no, can't use that b. Capital B for base times b of b times x minus c plus d on the outside. These are all the same things that we talked about before. This is going to be our vertical stretch. This is going to be a horizontal compression. This is going to be a horizontal shift. or translation. And this is going to be a vertical shift. Again, or translation if you prefer to use that word instead. So if we end up using something like y equals 2 times log base 1/3 of half x plus 7 minus 6. Right, just for something a little bit different. You know what? Screw it. Let's do 1/5 here just because. Right, we're going to get this to be pretty ugly, but like if you go with the transformation stuff that I've been talking about for years now, like this is not an issue. Okay, so what we're doing is we're saying that our function is going to have a vertical stretch factor of 2, a horizontal compression factor of 1/5, which means that it's going to be wider, but also taller from the 2. The base of 1/3 is going to be, again, what typical shape is this going to have? More or less, it's going to be like this. Right, so this is going to be log base 1/3 of x without any sort of modification to it whatsoever. There is also an asymptote at x equals 0. We didn't really mention it before, but anybody who's studied pre-calc before, you should know. Horizontal shift, this is going to the left 7, and this is going down 6. So I typically refer to this as using our origin point. So instead of being at Instead of being at 0, 0, our origin point has moved to be at -7, -6. And we don't need to go anywhere near that far. Yeah, that'll be right. Okay, so -7, -6 gets us to here, oops, as the origin point. Now it is really important that this is actually, right, at the origin point means that this is where the vertical asymptote is. Right, x equals -7. We can never have a 0 on the inside of our log. Like log of 0 doesn't make any sense. What exponent can you put on a 2, or in this case a third, in order to get 0 back? Right, there's just no way to do it. So x equals -7 is going to be a vertical asymptote. Okay. Then, normally, what happens is our initial point is typically at the location 1, 0. Right, the origin is usually 0, 0. The initial point is usually 1, 0, because we like doing this as b to the 0. Right, so b to the 0 is 1, and then the exponent we put on b is 0. So the exponent is the output, the exponential is the input. But that's not the case in this particular case, because what we've got now is that our horizontal compression factor is going to make this wider by a factor of 5. So what we do is, from our origin point, normally we go 1 space, but now we're going to go 5 times further. So 2, 3, 4, 5, until we get to -2, -6. Right, and the distance that we travel up and down isn't going to deviate because of the vertical stretch factor. Right, this is still going to get us our 0 vertical movement from our origin point. Because again, normally we just move straight to the right from the origin to the initial. And in this case, it's no different. We're just moving further than we normally would. All right, then from here, this is actually pretty easy. So, in our normal log base 1/3, what's happening is every time we move up 1, that's all right. Every time we move up 1, we're multiplying our x distance by 1/3. Right? Increase the exponent means we move up 1. But in this case, again, our vertical stretch factor is saying that we need to go taller, so our exponents are going to be doubled compared to how we normally do this. So here we're going to go, instead of going up 1, we're going to go up 2, and then find that distance, which is 1/3 as much as the distance between our origin and initial points. So go up 2, and then cut this distance, which is 5, yes, which is 5, into thirds. So this is going to be 1 2/3 is 5/3. So that's putting it right about there. Alternatively, you can kind of eyeball where thirds are. I hate doing thirds. It's one of the worst fractions to try to, like, gauge. Unless you have nicer other values, but we don't in this particular case. So anyway, this is about a third of the way back from our initial point back to the next point up. So this is going to be a negative 5. Oh, nope, nope, nope. The distance, right? The distance was negative 5, and now the distance is negative 5 over 3. But where does that put us actually, right? We can take that as starting from 7, negative 7, we're going to add 5/3. So that'd be, what, negative 21 plus 5 is going to be negative 16/3. Comma, and this is now at negative 4. And we can do the same again. So if we move up 2, and that's going to cut our horizontal distance by 1/3, or to 1/3 of the previous value. 1/3 of the current value. And that's going to put us at, now we are at 5/9 away from negative 7. So that's 63 minus 5 is going to be 58. Negative 58 ninths, comma, negative 2. And one more just for fun. So when we get up to y equals 0, that's going to cut that distance again by 1/3. So instead of being 5/9, that's going to be 5/27. And that's going to be a pain in the rear. 27 times 7 is going to be 189. So that's a negative 189 over 27 plus 5. So 184. Negative 184 over 27, comma 0. So that gets us in that point there. Okay. Then going the other direction. That's definitely to scale. I don't know what anybody's talking about. Terrible. Now when we move down 2, we're going to take the distance that we're currently at, which is 5, and we're going to triple it. So it's going to be 15 instead. So we move down 2. This is a distance of 5, 10, 15. Oops. Move down 2. This is going to be at 8, comma, negative 8. All right. The next one is going to have a horizontal distance that is triple what we have here, which is going to get us a distance of 45. So a distance of 45 from negative 7 is going to be positive 38. So we're that away. Right? It's going to be a ways. So if that was 10, this would be like 20, 30 is going to be 30 is going to be off the chart, so 38 is going to be significantly further. All right, starts moving like that. Alright, that's the sort of thing we got for this. Right, so if we have log base b of something that looks like m times n, right, how does that actually get used? How is it helpful to discuss like what this is? What's an alternate form? So one of the things that we can do is we can look at this instead of log base b of m times n. We could let m be equal to b to the a, and n be b to the... Oh, jeez. Just walked myself right into that one. Let m be b to the x, and n be b to the y. So what we've got here is really log of b to the x times b to the y, which is equal to log base b of b to the x plus y. Now we discussed earlier that the logarithm and exponential functions are inverses of each other. As long as they have the same base, then they can undo each other. So what exponent on a base of b gets us b raised to the x plus y? It's x plus y. Right? And then we just have to convert back. So x is going to be equal to, well, this is a little bit harder to look at, but if we reverse the form that we get for m equals b to the x, this is that the log base b, what exponent on a base of b gets us m? That's x. Okay, n equals b to the y is saying that we want, what is the exponent on a base of b that will get us n? That's y. b raised to the y is going to get us n. b raised to the x is going to get us m. So here, when we say x, we can replace that with log base b of m, plus we see y, that is log base b of n. And I'm hoping about half the viewers just went, that's why that works. I'm talking to you, YouTube. Okay, so then we could do the same thing with like any of the other log properties. We could say, okay, what happens when we have log base b of m to the n? We could do the same thing that we did before. So we're going to, again, let... Yo, Wither, how's it going? Let m be equal to b to the x. It's the same thing, right? So here, this is going to be that the log base b of b to the x raised to the n is going to be, well, that's log base b of b to the xn. right? Our exponents are going to be products of our exponent raised to an exponent, or an exponential raised to an exponent. So this is log base b of b to the xn. Well, redo. Oh, we're doing all right. So here, what exponent on a base of b gets us b to the xn? It's x times n. But then we just talked about this before, right? So we know that x is going to be equal to, right, the exponent on a base of b will get us m. So now we can replace x with log base b of m multiplied by n on the outside. So making it look a little bit nicer, normally we flip this around. So it's n times log base b of m. That way you're not possibly confusing, is n on the inside with m or is it not? Right, it's on the outside. So this is log base b of m raised to the n is going to be equal to n times log base b of m. Yeah, so we're doing all right. I should probably check that. Something might have hit the ground pretty hard. Hang on. No, we still got too long on the ad break. All right, hang on. Okay, never mind. That was just a dropped phone right above my head. So hit the subfloor and it echoed. Okay. So anyway, now we've got a way to talk about what happens when we're multiplying our exponentials on the inside of a log and how that compares to now adding our exponents. Because again, logarithms are exponents. So adding your adding your logarithm terms, adding your logarithmic terms here is identical to multiplying your exponentials, which then causes their exponents to add when they are of the same base. So, 2 to the 6th times 2 to the 8th is going to be 2 to the 14th, 6 plus 8. Right, so same deal's happening here. Let's also change these over, because... Boop. Right, same thing is happening here. We're saying that when our exponential is being raised to another power, then that's the same as multiplying our new exponent with our old exponent, log base b of m. Logarithms are exponents. So then what about log base b of m over n. Now I see that there are two ways to go. This could be the log base b of m times n to the negative first. Works. Or we could take this as log base b of, use the same m and n as defined up there. It's b to the x divided by b to the y. Right? Turn them into exponentials of the same base. So how do we deal with this? Well, when you dealt with this with exponential functions, this was talking about taking log base b of, this is now b to the x minus y. And now this is going to be x minus y. And as we redefine them up above, right, x is just going to be log base b of m, and this is going to be minus, y is just log base b of n. Alternatively, if we took this as log base b of m times n to the negative first, we can use both of those properties that we see there, and we could say, okay, well, now it's multiplied. So we can make this the log of base b of m plus log base b of n to the negative first. Then take the negative first that's in there as a power and knock that down front. So we've got log base b of m plus a negative 1 times or minus 1 times log base b of n. And that's the same thing. So now we can start defining more and more of our logarithmic thingies. All these logarithmic properties we can start defining more based on each other using some of these basic identities. Right. Then the only other one that we've mostly got is like b raised to the log base b of x. There's kind of two ways to go about it. One is to say that here we have an exponential term, which now has log base b of x in it. And these are, again, inverse functions of each other. So log base b of x is looking for the exponent on b that gets us x. And if the log base b of x is the exponent on b that gets us x, then that gets us x. it's a little weird, right? Like, okay, the log base b of x is this exponent on b, which gets us x. So this is defining, again, let's call it a. A is equal to log base b of x, can then be rewritten as the statement b to the a is equal to x. But we just said a is log base b of x. So it's going to give us the same thing. It's going to get us x. Absolutely. Yep. Do you have pen centers? Let's see if this works today. I know Enigma is very busy. Oh no. Enigma bot. Ah, boy. Where are we? Drive. Is it F? Streamer bot. Nope. Enigma bot. Nope. I did not name it any of those things.
It's me, the GC, and I'm here to tell ya, Paddy Power are treating punters like absolute royalty at Ascot this year. That's right, every Tom, Dick, Harry, and Megs. Right, someone bring me a champers and one of those posh sunbrollies. I'm sweating buckets.
Thanks, Gemma. Get the royal treatment.
Streamer bot.
Paddy Power.
You're listening to Biceps Track Glue. If you like what you hear, tap the banner and listen now on Spotify.
Okay, I'll see if I can open up StreamerBot from there, and I will see if I can give you the invitation link to Pen Centers if you don't already have it. But you can either go into Pen Center's Maths chat, or you can go to the Maths forum and add a... oh no. Oh no, I may not have it. That's not fair. Sorry. Here we go. Hopefully that will work. It may decide to be a jerk about it. Wow, okay. Really? Thought it was going so well. Yeah, my streamer bot may also not be working. Man. I was hoping it could at least auto-update or something. Alright, anyway. Cool. Alright, I'm going to run that 3-minute ad break, and then be right back. Let's see. Yeah. And set up an activity or two just to keep us moving and awake. So, we'll be back in 3 minutes. No. That's fine, Meowweather. The ads were coming up anyway, so like this is a good natural break point anyway. Now that I've figured out something on Discord, we'll be back in 3. So thanks for sticking around, and see you in a bit. Alrighty, welcome back everybody. Why is that all out of whack? Maybe not. Looks like it is bent weird, but maybe not. Right. A few weeks ago, we got some nice equipment for Escrima. We have now leather gloves, which are to protect our hands from the ridiculous amount of slapping that we end up doing with our sticks. So those are beneficial, although they really do not help with the grip. Like you can't actually hold on to the stick very well because these are giant. But they are kind of fun. They just need to be broken in a lot, I think, and I hardly ever use them, so it's one of the problems with it. But you know, you get that like Darth Vader look to it. It's pretty cool. And then the helmet, which goes on our faces here to make sure that we can actually throw these sticks around and smack each other in the grill instead of actually in the face. It's kind of fun. Yeah, my instructor bounced a couple off the grill just while I was standing around. He's like, "Oh, good, you got it on?" I'm like, "Yep." Yeah, just wanted to make sure it was on. All right, thanks. And with that, I also wanted to bring the lightweights up because these can end up getting around a lot quicker and be much more impressive in terms of speed and movement and stuff like that. They could, in fact, clack together and make a huge amount of noise, so I don't like that so much. But yep, there we go. These are also a bit shorter, so there's less chance of smashing into anything like the fan here. And our game's over here. So if anybody, again, isn't aware, Escrima is a Filipino martial art that uses sticks, also known as machetes. And actually people who do practice it actually use machetes. Very carefully, of course. You don't want to actually hurt your students. Good times. Let's see. There was... that one. Got a number of patterns. Welcome back. I'm not, of course, going to remember them all because we did so many. And also, I'm getting kind of popping motion in my wrist here. The unfortunate part of being old is that there's a lot of tendons that typically end up rubbing against each other. And so there's a lot of, for me anyway, there's a lot of like tendons that are coming together and then kind of snapping apart, which is very uncomfortable. I'm just hoping it doesn't end up ruining something. Let's see. So our typical, again, sticks to heaven. Then this week we did one where we're coming up and across rather than up and stopping. So this is like an upward block to try to parry a thrust that's coming straight in. Or, let's see, or if somebody else is trying to get smart and doing an upward cut, like to the face. Basically, it's the exact same identical motion. You're just blocking it. What else do we do? So we did this like... That's the other thing about these is, I don't know if you can hear it, but they whoosh through the air really nicely. Because I can get a mixture of speed and power with these that I really can't with the ironwood, which are 4 times heavier, or the polycarbonate, which are twice as heavy and longer, which typically ends up with getting less motion, less overall, more overall power, but less ability to put energy into it. Yeah. So we've got I'm not quite doing this right. Here we go. It's out here that I'm forgetting. Anyway, so yeah, we've got a number of interesting patterns. I'm also trying not to like let go of the stick. Basically, I'm holding onto it with like the inside of my thumb whenever I'm trying to do like this motion, and realistically you should like hold on to it entirely and make your entire wrist turn. But again, being almost 43 years old, it tends to not work terribly well. Forward, I'm not quite as reliable with it. I gotta be careful. I am still pretty out of range here, so that's good. Back windows. I've got heavy curtains on it, so I'm not gonna like bash a window open. Yeah, we did some other interesting stuff, and now I'm trying to... I'm going to do another one on Thursday, so another class on Thursday. So we'll see how it goes, but... Yeah, this is the awkward one. Where you try to whip it around both times, and then get it back to your shoulders. Problem is that my wrists don't want to turn this way, especially. Anyway. So, if we want to get back into it, so, whether were you able to get into Penn Center's Discord? I've been having trouble with some the invite links sometimes. So, okay, good. So yeah, if you see over on the probably about halfway down, maybe a little less, math channels is in there. Cool. We will also go for one more redeem while we're here. Either one. So if you just want like, yeah, it doesn't really matter. But I would probably, I don't know, I'd probably go with Forum. That way we can just kind of like keep it self-contained. Like if you need anybody to help you, either of those places will work, you know, most of the time. Where did I put it over here. All right. So the redeem AI is by here's a book from John Gould called Maine Lingo, A Wicked Good Guide to Yankee Vernacular. And growing up in New Hampshire, I heard a lot of people who had, you know, Bostonian and New Hampshire and Maine accents. Naturally, nobody has an accent. What are you talking about? But the Down East Maine is up near the location called Bar Harbor or Bahava. It was probably about a 3 to 4 hour drive from where I lived, and I hadn't actually gone to like Bar Harbor proper until I was on my honeymoon, where we needed to leave Bar Harbor via the Cat, which was a catamaran ferry. So I had two like pontoons essentially, and then it went so fast through the water that it actually caused a rooster tail out the back. So there was a very interesting boat. They unfortunately discontinued it sometime in the last 20 years. But anyway, there was a guy who did a series of LPs with his friend. They did master's degrees at Yale, I think it was, in basically the storytelling style of Down East Maine, people from Down East Maine, and they like went out and listened to people and recorded their stories, and then eventually they wrote their own and put them on this LP, taking bits and pieces from other people's stories, reimagining things, and basically creating an entire town called Millinocket, which is fake. It's not a real town, but it sounds realistic enough. So they created a bunch of characters to fill Millinocket, Maine, and ended up releasing a series of LPs called Bert and I, or Bert and I, which was their culmination of all of their research. I grew up with this sort of stuff, so it was kind of interesting. So I decided that I would bring a little piece of Millinocket to the rest of the world. Today I just kind of grabbed a page here semi at random. Yeah. Okay, we'll do this one. The phrase is artistic purposes. The full phrase is mechanical and artistic purposes, and it comes from Maine's old dry law. Booze was outlawed except as prescribed by by a friendly and understanding old family physician, or when it was to be used for mechanical and artistic purposes. This latitude was often a blessing. In Maine conversation, artistic purposes means little more than devious intentions, a high-sounding substitute for something less than noble. Hank Woodbury, for example, used to go down to Boston on the steam cars for what he called artistic purposes. So that's going to be tonight's. I believe those are to be redeemed not more than once every 20 minutes or something like that. So if anybody else wants another word at some point, feel free to throw that one in there. Okay, so let's get the glove back on. At some point, I do actually want to, like, do a Bert and I stream, but it's going to be a while. I've got to get all the stories and then put them in order again. Some of them being a little uncouth. Oh my. Let's see. So a couple of extra little problems here while we wait. Solve for x. We got 4 to the x is equal to 2 to the x plus 3. Now this seems to be quite odd. Because you probably wouldn't get something that is then like 4 to the x is equal to 2 to the x plus 3. One might think immediately, oh no, that's going to be like really nasty. The good news is that... Nope, never mind. Uh, yeah, I tried doing... Wow, okay. So the obvious one here is going to be if x were 0, then we get 2 to the 0 is 1 plus 3 is equal to, but here then we get 1. So that would not work. So that's kind of wishful thinking. So I don't think this is going to be pretty nice. Oh no, no good news? What's that? So for this one, I think it's going to end up being something pretty awkward. Like, it could end up being a log base 2, which then would just bring down whatever x is for each of those things. So in theory, that might work as well. The other thing to do would be to say, all right, let's assume for a moment that this 4 to the x can be written as 2 to the, and then here this could be 2x. So that's one good way to do it. Yeah, struggle all the time with them. Yeah. That's why they exist. Gotta struggle a little bit. Or we could rewrite this as 2 to the x parentheses squared. Okay, and then if we shift everything over the other direction, this means that we now have a minus 2x minus 3 is equal to 0. And if we want to be, like, if we want to connect this to stuff we were working on earlier, the easiest way to do it would be to say let 2 to the x just equal a. So now we've got a squared minus a minus 3 equals 0. That's way easier. Right, so now we can solve a quadratic rather than having to solve a exponential or a quadratic exponential. We'll do this one step at a time. Right, so we got to solve this first. So we take negative 3, we say what are the factors? It's 1 and 3. The larger of the two factors must be negative because when you add them up you have to get a negative. And they have to have opposite signs because when you multiply them together they have to give you a negative product. So negative product means opposite signs. These quite clearly add to negative 2, which is not the number we have here. Right, so we can't use standard factorization. We have to use the quadratic formula or some other method that you might be able to come up with. Completing the square is an option. I don't really like it or enjoy it all that much. So generally speaking, I don't do it. But it is a perfectly worthy pursuit if you want to go for it. Like I said, I just don't like it. So for this one, we could say that a is equal to, so negative middle term is negative 1, plus or minus square root, b squared is, well, negative 1 squared, minus 4 times a is 1 times c is negative 3. All over 2 times a, which is 1 in this case. Just sound of fond. Good evening and welcome back. How's it going? Yeah. I know it's not hard, it's just a matter of, like, I don't typically like doing it. 1 plus or minus square root 1 plus 12. So we get the square root of 13 all over 2 there. One plus or minus square root of 13 all over 2. Okay. Now when we do this, we're going to have to look at this and say, can we get any of these values as 2 to a power? Yep. So this is equal to 2 to the x, which means, right, the negative version doesn't work. Because we end up getting 1 minus the square root of 13, which is bigger than 1, so that would get us a negative value. And then a negative cannot be equal to 2 raised to something. So this can only be 1 plus the square root of 13 all over 2. So x is going to be equal to log base 2 of 1 plus root 13 all over 2. You could, in theory, separate out the 2 at the bottom there. That could be equal to log base 2 of 1 plus the square root of 13 minus, because again we did that stuff up there, which was if you have a division sign on the inside, that's going to break it down and make it a subtraction of the denominator. So log base 2 of 2, which is going to be equal to 1. Whichever version of this you want to put out there, as long as it makes sense to everybody, you're good. Right, and I guess we should, in theory, just plug it in to make sure it actually works and isn't a false answer. Because that happens sometimes. Okay, so we say we want to take, right, 1 plus 13 square rooted divided by 2. Take the log with base 2 of that. Curses. It's going to be equal to about 1.20337. Less. Right, because root 13 is only 3 and change. So we divide that by 2, it's going to be like 1.5. And then we're doing log base 2 of 1.5. 2 and a third. Damn. 3. Oh, 3 point something. Plus 1 is 4 point something. Divided by 2 is 2 point something. Yeah. Okay. I'm alright. Yeah, it's all good. I mean, keeping in mind, right? This is supposed to be for GRE, so this is for graduate student or people intending to be graduate students doing something that they need math for in some way, shape, or form. Add that to the memory. Okay, then we go back and we say, right, this is what we get. Cool. Yeah, this is like the basic GRE math test. This is just like section 1. So we've been working on this for a few nights, just to get like the basic stuff out of the way. Yeah, GRE math test. Granted, this is from 2002, but I don't think it's changed all that much. Maybe so. Okay, we got that number. We want to do 4 raised to that number. 4 raised to memory equals, this is 5.30277756 and change. Okay, and then we go to the other side and we say, what is 2 raised to that power? And we get 2.3027756377. Nice. Add 3, it makes it 5. Yeah. So this does actually work out. Excellent. All right. Next one. If x squared plus y squared is equal to 14xy, then log of k times x plus y is equal to 1/2 log x plus log y. For some constant k, find the value of k. So if we start with log of k times x plus y is equal to 1/2 log x plus log y. The way I would want to start, I think, is make this a 2 log k x plus y like that. Is equal to, this is going to get us log of xy. This will get us log k squared x plus y parentheses squared is equal to log xy. Okay, we're going to raise 10 to both of those sides. That's then going to get rid of our logs. So we end up with k squared times x plus y parentheses squared is equal to xy. The x plus y squared bit, k squared times x squared plus 2xy plus y squared is equal to xy. We did say up top x squared plus y squared was 14xy. So this is going to be k squared times 2xy plus x squared plus y squared is 14xy. Is xy from that side. So k squared times 16xy is equal to xy. Divide by xy, provided neither of them is 0. I think we're good there. So x squared will multiply 16 onto both sides is equal to 1/16. So therefore k is, absolute value of k is going to be 1/4. So k is going to be plus or minus 1/4. Unless it said positive. Okay. X and Y must be positive, right? X is greater than 0, Y is greater than 0. Therefore, X plus Y is greater than 0. Therefore, K must be greater than 0. Right, so we're going to eliminate the negative case. And K must therefore be positive 1/4. If anyone has any questions, let me know. Meowether, if you get yours into Discord, let me know. Okay. So log base xy times x to the y simplify times 1 plus log base x of y. Okay. So this is going to do same kinds of things again. X by itself must be greater than 0, which then also means that this y here must be greater than 0, and I guess, right, that there, y must be greater than 0.
You get to focus on the music, explore a vast catalogue of millions of songs without hearing ads, or download your playlists to listen to them anywhere.
Okay.
You can also play your favorite songs at any
I think we want to build these up first rather than breaking them down. So this is going to be log base xy of x to the y times this, right? 1 can be equivalent to log base x of x. So this is now log base x of, if we multiply the arguments together, we get xy. Okay, slightly awkward, but this will work. We take log base x of xy raised to the log base xy of x to the y. Right, when we multiply, that's the same as, okay, when two exponents are multiplied, that's the same as their associated exponentials being each other's exponent and base, in whichever order we want on top of that. So if we wanted to, we could have gone the other way. And in fact, right, let's try the other way next. Log base xy of x to the y raised to log base x of xy. Ugh. It's the edge of my screen. Okay, so this one, we have the base xy being raised to the log base xy, which one of our properties from earlier said that that is going to cause those two terms to end up, hate the term cancel each other out, but you know what I mean. They are inverse operations of each other, and so they both go away. Again, this is saying log base xy is the exponent for which the base xy is going to have x to the y as its result. So therefore, x to the y raised to that particular exponent is going to cause us to get x raised to the y. And then we can make the same argument here. The log base x is saying we want the exponent on a base of x that's going to get us x to the y, so therefore it's just y. Okay, and then over here, same deal. This is x to the y being raised to the log base x of xy. Actually, we can't do that argument just yet, but we're almost there. This is going to say that our exponential being raised to another power is going to multiply those exponents together. So we end up getting x raised to the y log base x of xy, which is going to make us get x raised to the log base x of xy to the y. Gotta give all of that, right? Exponent of y goes to xy. Which then, in turn, now we get x raised to log base x. So again, the log with base x is the exponent which, when x is raised to this particular exponent, it's going to get us xy to the y. Therefore, x raised to the log base x of xy to the y is going to get us xy to the y. Again, we can go with inverse operations argument, or we could go with the fact that logs are exponents, which again give you the result of what's in the middle, what's in the argument. Here, again, log base xy is the exponent which gets us xy to the y on a base of xy. Therefore, it is y. So either way we go with this, either argument you want to use, they're both valid. If you want to simplify all this stuff, turn one of them into the other one's exponent. It almost never works out this nicely, but this was one that somebody like manufactured in order to drop out in just the right way. Alright, that's the last one on that page. Nice. Alright. So close. This one, which? The thing I just did? All right. how log was defined as part of some formal power series. Well, took them a while to get there. Getting from Napier to Brooke Taylor. All right. So we start working with never seen the algebraic construction for logs. Like how Napier started them, or like how they got formalized. I mean, how Napier did it, sort of aligned with what I was doing earlier, but sorry, the mat that I'm sitting on is not properly aligned. That's starting to get above my pay grade. Which, I mean, granted, like, I must have taken that class at some point, right? But that's not even necessarily true, because I was originally a math ed major. And then I didn't take analysis until master's level, and that was like real and complex analysis, which were very different from, I think, the junior level analysis class that like my spouse took. So geometry comes originally from Greek, which really has two roots to it, right? And this is kind of the same as it works with English, where you have this geo, or geo, at the front, which tells us that we're dealing with Earth. And then the metria part, that's at the end, really is talking about the act of measuring. So geometria really means earth measure. If anybody actually speaks Greek, you can correct me, but as near as I can tell, in the ways that I have, you know, broken down things and tried to study individual parts of all this stuff, yeah, it looks right. And in doing so, we had a few individual people who made major strides toward this. So we had Eratosthenes, who heard tell of a well in saw the definition, never mind, it's defined as, yeah, okay. So Eratosthenes heard of a well. He lived in Cyrene, and he heard of a well in Alexandria, which on one particular day of the year, and in fact it would be, if it's within the tropics, it would be 2, so 1 as the Earth is tilting toward the sun, putting the northern hemisphere into summer, and then again once more just after the solstice as it's coming back. Yeah, with fancy language, of course. So, I don't know, where is Alexandria from that perspective? Whoa. There we go. Boo. Give me the latitude, longitude coordinates. Why are you making me go to the wiki? No, it's 31 degrees north, so it doesn't actually make it. Well, that's interesting. That's unfortunate for that story. Oh no. No, not there. Here. Which might be stupid because 22 north. Okay, so like Aswan is pretty close. What's that one? Abu Simbel is pretty close to Aswan, and fairly close south of, but pretty close to the Tropic of Cancer. Was Alexandria the Massachusetts of today's world? I mean, in terms of like Boston, where you've got like the historical sites of where the country was like first really founded, where you've got a bunch of libraries that are trying to save all the information. Yeah, sort of. I would probably liken it more to in terms of like importance, especially to the Greek Empire, probably closer to New York. Not really. So, yes, in terms of if they have a good visual ability, if they can see things, or like imagine shapes and see how things work, then I think that like their ability to study geometry might actually reflect their ability within mathematics. But keeping in mind that like there are two really kind of separate pieces to it, right? You've got your logic and reasoning, and then you've also got your notational ability. So somebody could be absolutely brilliant and be complete crap at the notation. So I would hesitate to say like, oh, it's going to be, you know, a big indicator in terms of their ability. Like, not really. So yeah, Eratosthenes allegedly had a deep well in, allegedly, Alexandria. It is not below the Tropic of Cancer. So therefore, it should not actually have the sun should not be literally directly overhead. It'll be off by 7 degrees. But that does mean if the well was off by a certain, degree measure, then who knows? It could also be that they found another place further south and worked off of that. But either way, if you've ever been within the tropics, I highly recommend checking it out on a day when the sun is in fact directly overhead. So check your location where you're going. My father used to live in British Virgin Islands for 10 years or so, and he and my mom would go out on that particular day. There were again 2 days. The sun's coming one way and then back the other. So there's 2 days during the year where you have literally no shadow because the sun is directly overhead. You only cast a shadow straight down, and posts that are in the ground won't have a shadow because they have no overhanging part. The sun is coming down around it, and so every side of it is equally lit. A lot of people say it's one of the weirdest feelings that you can get because nothing has a shadow unless if you stand like this, you have a very minimal shadow. So anyway, Eratosthenes was in Cyrene, measured the angle of the sun, went to Alexandria, measured the angle of the sun on the same day during 2 different years, or had multiple people measure it at the same day, same time, etc. And they figured out, or what the zenith, the absolute height of the sun was at local noon. So they measured angles to the sun and were able to figure out what the angle of the Earth was, and then because of that, our ads are going to start here in a second. Because of that, they were able to figure out what the arc length was. Or they knew what the arc length was. There we go. They were able to figure out what the whole size of the Earth was from that. All right, we'll be back in 3 minutes. Sorry about that. Welcome to everybody coming back in. I redeemed for myself Dost Thou in Hoist? One of the more ridiculous memes, but it just really stuck with me. It was that picture of... it was the picture of that guy in like 1700s garb that's going like that. I forget the guy's name. The one with the jaunty hat. I couldn't tell if he had long hair or a white wig or what, but... How's it going, Phobos? Woo! Yes. Hopefully don't drop these on myself when my arms fail. It's all good. Whoop. Too far back. Well, thank you. Thank you, Phobos. I've got to get better redeems for those. I was so close. No way. I'd never be able to get any amount. I mean, I'd never be able to sustain it. Be like, okay, let's go down to 5 pounds. Yeah. Alright, 15s. I don't want to collapse with these things on me. even if they are only 15 pounds now. I was doing a regimen with my spouse, and it was called Shailene Extreme. If you've ever heard of it, oh my god, that woman is torturer. So the trick was that you get as heavy a weight as you could possibly get, and like do whatever exercise it is as many times as possible until your muscles literally fail. And then you move down to like the next one that you have in your house. And you just keep repeating until you fail and fail and fail again and again and again. Because eventually your muscles just can't handle it. Doesn't matter how light it is. I guess like 5 pounds you could probably do for quite a long time. You must have done something close to what I got, right? Maybe in a different direction, but... Did you get masters? Or bachelor's in math? Computer science. Oh, and math, yeah. Okay. So Eratosthenes worked out what alpha was for the make the computers go brr, yeah. Eratosthenes worked out what the alpha was for Earth. So he figured out that, you know, when the sun is in the sky so that you can see it in the well at Alexandria, and you could see it in the well at Cyrene, you know, he figured it out. I guess it's not obvious. Yeah, whatever. He worked out the angles to the sun from where he was in each of these locations, which effectively gives him latitude. And then he said, these locations are roughly speaking north-south-ish of each other, and worked out, he knew how far apart they were, in this case S, and he said, okay, if we've got now alpha over 360 degrees is going to be the same proportion. This was all done in words because none of them had this. Our particular arc length, the distance that we've gone around the Earth between Cyrene and Alexandria, is going to be compared similarly in the same ratio with the circumference of the entire Earth. Yeah, sometimes it does feel like that. By take, what do you mean? Bunda the big bunda. If I encountered something big in math or foundational, how would I release it? Sort of, Phobos. Well, I'd probably get it checked by a few close friends before I did any sort of mass release, certainly. And then, I don't know. Depends on what it is, right? So, like, if it's just some piece of math that I like, that I've been working on for a long time, that sort of thing, I would probably, like, work out a, make a paper and then release it to probably like Quanta Archive and a couple other places. If it was like a contest thing, I'd probably release it to... Man, I don't know. I mean, the company that's putting the prize out, and then probably a few other, like maybe university presses or something like that. Mass release, send it to everybody. I mean, I'd need more information on that, because, like... Yeah, I would definitely not want to send it to, like, post a video on YouTube and start calling all of the newspapers and being like, I just broke mathematics. Like, no. 1,000 pages book like EGA? Okay. I mean, if it was something like that, if it was something that could potentially destabilize the sociopolitical climate of the entire world, then it's possible, like P versus NP, it is possible that somebody would catch whiff of it before I released it and been like, hey, you know, you probably should classify that. And realistically, they would know about it. They would know about it before, like, everybody. Well, I don't think I would get a chance to decide. I think it would be decided for me by somebody who actually has the clearance level. Thrive on chaos. Yeah, but at the same time, it depends on what it is. If it is something, for instance, like P versus NP, and anybody would then have access to our nuclear arsenal, I think I would rather not put it out there. I mean, granted, I'm sure that the US government and whoever else is working on, like, you know, quantum encryption and all sorts of cool stuff, so that it would be nearly impossible to make that, break the encryption. But nonetheless. Alright, so Eratosthenes then worked out exactly how to make all this work. He got that the circumference of the Earth was, roughly speaking, 250,000 stadia, which, given the approximate estimate that a stadium is a certain number of meters, kilometers, whatever, his estimation was decent to approximately 2.5%. So, like, not too bad, especially given how long ago this was. Eratosthenes was like in the 240s BCE. So so we're talking like 2300 years ago. Eratosthenes already also knew that the planet was approximately spherical shaped anyway, so they estimated it. He estimated it to, you know, a reasonable degree. And again, pretty close to 2.5% error. Pretty decent. All right. See you later, Phobos. Have a good night. Afternoon, I guess. Nah, your night. Yeah. I do not have Bertrand Russell's true foundation of mathematics there, but formalization and logic did not pick that one up. All right, so the basis of geometry then becomes the individual structures. of hell. Nope. Hell's this? Oh, flourished. Yeah, and you know, the you know, in all likelihood, my family probably would have been maybe. Let's see, my father probably would have been a woodworker in like any other time period, because he got into woodworking once he had a little bit of money. He just bought himself like an entire wood shop. So it's pretty obvious what he liked to do, no matter what, you know, anything else is going on. He still does all sorts of projects and stuff now that he's retired from his main job. I mean, realistically, he retired from his main job probably around my age, and then he was working as a flight instructor for a very long time. Yeah, it all depends on when and where. So like most of my family's coming from, his side is coming mostly from like Eastern Europe and partially from British Isles. My mother's family is like almost exclusively from British Isles. So it's actually really funny being back here. Everyone also has a way more relaxed attitude. So Euclid was about 300 BCE, so roughly speaking 2300 years ago. And Euclid was all about formalization of mathematics and geometry in particular. He started out with, you know, what are all the definitions of things we're allowed to use, and then we'll expand upon that as we go. And so we start out with just individual points, which are locations in space. They have no breadth, width, or depth. They are just existing as individual locations. And then if you put two of them together, you're then able to connect them with a line. Now, asterisk, they did call this a line. So even if it is finite in length, they called it lines. We now call them line segments. So here's the thing, right? We have evidence that geometry, generally speaking, has been done in Mesopotamia, in the Babylonian Empire, and all the way back through Egypt for millennia. We don't have any record of it being formalized before Euclid. So there's plenty of evidence that people were doing it. It's just that nobody was sitting down and being like, "Hey, we've got to work this out for like the good of all humanity." That wasn't really their thing. The Babylonians had for instance, make them right edges. The Babylonians, for example, had a clay tablet that was found. I mean, I'm going to say recently, but by recently, I mean like 20 years ago. No. Should definitely look these up. But there was a Babylonian clay tablet that was found. Had something like this on it that was like, find the ratio of the areas of the triangle to the circles, and then from the circle, like all four circles to the whole square. So this is I mean, is it hard to believe that Bertrand Russell was the first one to like extremely well-defined mathematics on that ridiculous idea that if some future civilization or aliens were to come to Earth, that they might be able to understand our mathematics based on his work? Yeah. I saw this one on Marcus de Soto's The Story of Maths, which came out in like 2008 or something like that. Was really nice. They were talking about the Rhine Papyrus. They were talking about various other things, but this is the one clay tablet that they pulled out and were discussing. It was a German mathematician slash historian who was going over this particular tablet. Yeah. Apart from using just different language, which is also somewhat impenetrable to even read by itself. So I ended up, I don't know how don't know when exactly you came to the stream, but nonetheless, I was gifted a number of older books. So, Tensor Calc by Singe and Schilt. Elementary Partial Differential Equations by Berg and McGregor. And Introduction to Partial Differential Equations with Applications by Zakmanoglu and Tho. So there's like all of these books. I got 10 boxes, or like that big, just filled with math books that this professor had gained over his life. His son was cleaning out his attic because he was going to go live in a assisted facility, and just, you know, he was cleaning stuff out and trying to figure out what to do with it. I found a book by, I think it was John von Neumann, and I looked at it and it was like second or third edition, and I'm like, ooh. I returned it to him. I was like, I feel really bad taking this from you and not, like, you know, you told me do whatever you want with these, and I'm like, I feel uncomfortable having this book in my house. It's probably worth $750 by itself. You should have this because, you know, it's yours. And he's like, no, I mean, I gave it to you. I'm like, dude. So he took it back, maybe under duress, but he's also an engineer, so it was like, this would be really cool to have like as a conversation piece on my desk. I'm like, please lock it. How's it going, Zach? Happy Monday to you too. How has your Monday been? Things have been going pretty well over here. It is just reaching 1 o'clock now, so we're going to probably wrap up last couple of bits. Probably hit another couple of thoughts here and then probably duck out. But really appreciate everybody coming in. So Euclid was talking about like building from basic foundations. We start with points. We build those points into a line. We build those lines into then, in this case, angles. And then also into planar shapes. 2 doctors today? Oh, man. I mean, you are one now, so like... Yeah, your doctor-to-doctor interaction, exactly. We're finally making appointments to get to our dentist over here. It's probably something we should have done a long time ago. It's been a year for anybody else, and it's been multiple for me. So I've got some pretty nice holes in my teeth that need to be filled. None of them are actually getting infected or painful, so that's good. Doctoral. Right, so in doing this, Euclid then defines our 4 main postulates that everybody knows and loves. So after defining what you're allowed to do or what objects you have in space, he says that the postulates, which are things that have to just be stated, will exist, right? Will occur in this space, whatever it is. You know, 1, we have to be able to draw a straight line from any point to any other point. Makes sense. This is, again, planar geometry. 2 to produce a finite straight line continuously in a straight line. So if I already have a line, then we can continue it as long as we want to in either direction. 3, to describe a circle with any center and distance. Okay, so we've just drawn circles up there approximately. And as long as you give me a location for the center and a distance that it has, called the radius, then we can define a circle uniquely compared to any other circle. 4, all right angles are equal to each other. So no matter if I draw a right angle over here or a right angle over there, those are the same thing. All right, fair enough. 5th postulate, that if a straight line falling on 2 straight lines make the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, will meet on that side where the angles are less than the 2 right angles. What? So you got these 4 specific definitions that are like almost obvious that you're allowed to do all those things. Standardizing the measurement of angles without a protractor, yeah. Right, that if we draw 2 straight lines with a third line crossing it, and it turns out that these 2 lines actually, if produced indefinitely, end up meeting somewhere, then it turns out that these 2 angles will sum to less than 180 degrees or 2 right angles. Now, a lot of people are like, well, why do we even need this if it's just planar geometry? And the point is that what if it's not? What if you're just defining the space in which things live and what kinds of things are allowed? If we omit the 5th postulate, then actually what we have is 3 different possibilities. Right, our 2 right, we have our 2 lines which end up meeting on this particular side, and then the sums of those angles end up being less than 180 degrees. This is telling us that what we're making here is that we have a triangle on one side, and the other side is going to be geometrically open. So in this particular case, what we've created is this planar or Euclidean geometry. Slightly ironic because Euclid knew of the other 2 possibilities. Right? The other is that if you draw 2 straight lines, there is the possibility that if you have one side that has a, significantly smaller angles than 2 right angles, you could still have 2 sides that are completely open. Now, this wasn't really formalized until the 1800s. So this is Janos Bolyai and Nikolai Lobachevsky, who were the ones to formalize what we now call hyperbolic geometry. And the other way that we could have this happen is if we're on a curved surface and you draw two straight lines, but it's curved opposite the way that hyperbolic is. Again, our angles could be whatever you want, but here, because of the way the straight lines work, you get triangles on both sides. And this will happen on spherical geometry. Now maybe these are just categories of larger sets. There could very well be other smaller types of geometry that are more specific, but you know, more generally specific, or wow, no. If we're talking like very generally, this has no curvature. This has positive, I think, curvature. And this has negative curvature. I was going to go with Paul Harvey, Zach. Now you know the rest of the story. Hilbert's version is the most accepted. Yeah. Field is a local ring. All right. Yeah. So I think that the idea was that Gauss was like, kind of did, pulled a Newton, where he was just like, yeah, I thought about that years ago, but like, no, you know what? I haven't. I'm going to have to look that up. Well, all right then. 1953. Goodness. Oops. So anyway, yeah, depending on whether your curvature, the space curvature, is positive, negative, or nothing, and I mean, mathematicians always go with, is something positive, negative, or zero? Like, that's just kind of a logical extension of what else we're trying to deal with. Euclidean space is basically just a specific example. We have examples of, all of those curvatures existing in real life. Not necessarily like space, but surfaces that we've got all over the place. You've got the hyperbolic geometry on, well, I mean, I have a game called Hyperbolica. We played here on the stream a couple of times. Not very often, but there's other cool stuff that's in there. Fancier reformulation, cat K-spaces by Gromov. I am positive that I will not understand a single bit of it. But yeah, there's all sorts of cool stuff. And the fifth postulate, like, this means, at the very least, that Euclid understood that there were these three different kinds of possible curvature that could exist. Or at the very least, he understood positive curvature because, Earth. He understood planar, no curvature, because he did planar geometry. And he probably at least understood that negative curvature existed, even if he couldn't necessarily work it out exactly. Maybe there was, some attempts to do some hyperbolic geometry on the inside of curved objects rather than on the outside of curved objects. But, I don't know how things worked back then. All right. I think it's going to be about that time. So, if anyone is planning on asking some questions, feel free. Come on back on Wednesday. We'll have more question and answer time. I'll do more GRE stuff. We'll do whatever we feel like. So, hope you all have a good couple of days. Probably going to be working on either Elite Dangerous or YouTube stuff for my channels in order to get some of the other nonsense out there. Zach's not on. Those are our YouTube channels. Obi-Wan Pez is the gaming content. And Simplex Pachinko 6542 is our math content. Jigsaw Scam Baits is on. That's pretty fun. What new math do I plan on learning? So, I do want to eventually try and understand tensor calc better, but I keep getting stuck on chapter 3 of Grinfeld's tensor calc book, which is maybe a little ridiculous or something, but it's fine. Okay. I just need to make a decision. Let's go over and nobody's really doing academics at the moment. No. I mean, nobody. Casey Snow Art or Shane McInnes? I don't think so, but let's try. Miniatures and models for Shane, and Casey Snow Art does art. No, okay. What is Casey up to today? Whew. Looks like Dromaeosauri or something of the sort that are taking flaming sticks through the forest. Oh, Pyroraptors. There we go. Hell yeah, let's go for it. Pyroraptors, living up to their name. Alright, so I'll see you all on Wednesday, and probably be working on some other stuff offline tomorrow, but, I'll be around in the Discord, and I'll head over to Don's probably, because he'll be doing, Don will be doing math tomorrow. So, see you all soon. My name is Obi-Wan Pez. This is N Simplex Pachinko. See you next time.